All right, chemistry students, this is the last video for chapter 9 that is going to go over properties of solutions. And those are specifically called colligative properties, okay? So it's a fancy term for this property holds true no matter what the solute is. So remember, this whole chapter is about solutions, and you have a solute that's mixed into a solvent, generating the entire solution, okay? So colligative properties, these properties are true. It's kind of like if you ever watched that old cartoon, the coyote chasing the roadrunner. No matter what the roadrunner did or the coyote did, they could never, the coyote can't ever catch the roadrunner. That holds true regardless of what method the coyote used to try to catch the roadrunner. Okay, that's what the colligative properties are like. It does not depend on the type of solute. These are patterns that are true of solutions as long as you've got, you're comparing, say, empty solvent to solvent plus the presence of solute. And these are the 4 properties listed at the bottom. And what you're going to see is empty solvent without the solute added. There's going to be a difference between the way that acts versus when you have a solution, the presence of the solute. So you're going to see that vapor pressure gets lowered. You're going to see in the presence of a solute. And the more solute added, generally the lower the vapor pressure is. And we're going to go through each of these. We're going to define them on the subsequent slides. We're going to see that the freezing point of the substance gets lowered. We're going to see that the boiling point of a substance with solute present actually gets higher. And then osmotic pressure is actually a pressure value, and that's a different section, but we're going to get into that, so I'm not going to put a lowered or higher on it. Okay, so let's go through these properties one by one. We're going to start with vapor pressure lowering. Okay, so this is where it'll really help if you think like you're in the beaker. Okay, so it's sort of what's in the beaker, what's sort of condition 1, and then what happens if I make a solution in the beaker, and now I've got condition 2. Okay, so here's an empty a beaker. It's not empty, but it's got solvent alone. So pure solvent. What is vapor pressure? So vapor pressure is down at the bottom of the beaker. You would have the liquid of this pure solvent. Okay, and in general, there is always a little bit of the gas form. So up here, this is the gas form. All right. So it's just a small amount of vapor. You make a note, vapor gas, okay? And normally in many substances, there's a liquid vapor equilibrium that is going on as the solvent is just sitting in the beaker, okay? That equilibrium has a certain amount of pressure because remember, gas particles hit the wall of the container. They could potentially hit each other, and then they're also hitting the liquid beneath the gas, okay? That is your vapor pressure, the pressure of a gas over its liquid form. So once again, this is pure, just to make a note, pure solvent in that beaker. Okay, solvent, sorry, forgot the T. Okay? So what happens if we actually dissolve a solute in there? Okay? So the main thing you do need to know is that the vapor pressure, the value of that pressure is going to be lowered, okay? You can calculate that. Sometimes it's actually easier to see maybe on a graph. You could see it lowered in the presence of more and more solute, but we're not going to do that in here, okay? Excuse me, in the video. These red spheres on the bottom beakers are solute present. And what you see is when solute is added, the amount of vapor is reduced, okay? So you see this green arrow. I'm going to erase. There's a downward green arrow. In other words, more of the vapor returns back into the liquid state until equilibrium is reestablished, and that's why these 2 green arrows in the beaker on the right are even, okay? So that is the concept. Essentially, you add a solute, in this case the red spheres, and the gas is going to get reduced back down to the liquid. It's going to change back to the liquid state, okay? By reduce, I mean it's just going down. Sorry, going down in this case, from the top of the beaker in the gas to the bottom of the beaker in the liquid, okay? So these images did not come from your book. This image on the left that I just put in here, this is the one from your book where you could actually use a little tube on the right, and you have an image with solute on the left and an image with just plain solvent on the right. And you can see the amount of pressure measured in a height distance on this tube on the right, and the height distance on the right, pure solvent, okay, pure solvent, that distance is higher than this distance here that I'm trying to kind of box in. Keep forgetting my T and my solvent, pure solvent, whereas if we start to make a solution or we add solute, we have lowered the height, this height, on the little measuring tube, okay? So that would be an instrument you could use in the lab to actually measure vapor pressure with an exact unit. But you really just need to know that in the presence of a solute, vapor pressure, what it is, and that it's lowered in the presence of a solute, okay? So the second colligative property was freezing point, okay? You already know this concept based on putting ice on the roads. That's what I added at the very beginning. I said, why is salt added to icing roads? This is why. Because let's say we deal in Celsius usually in chemistry class, but let's just say it's freezing out, it's 32 degrees Fahrenheit, or maybe let's even lower it to 30 degrees Fahrenheit. It's very, very cold. Well, the water that's on the roads is going to turn to ice, and that's risky for driving. So if we can somehow lower that value to, say, 25 degrees Fahrenheit, or maybe lower it to -4 Celsius, then that would be more likely to be in the water liquid stage than in the ice form, and that's safer on the roads, okay? So that is this freezing point depression. This concept is exactly what's happening when salt and sand are put on the roads when it's freezing out. So you can calculate all of these, and this one I am going to show you how to calculate, but you do need to know in the presence of a solute, the freezing point of a substance, whatever the solvent is lowered as long as you've got some solute present, okay? And that can be calculated, okay? So this is the expression for the calculation. You're going to have the change in temperature, and this F stands for freezing point, okay? So what we're going to see is there's going to be a similar looking formula, except there's going to be a B for boiling point, okay? And these units are in degrees Celsius. And then we're going to have some constant, okay? So every solvent, there's a table in your book that can show water has a certain KF value. Every solvent has a KF value that's generally known. The common solvents do. So this is in units of degrees Celsius per molality, or if you actually listed out the molality, you could have degrees Celsius kilogram per mole, okay? So that's a known value. So that value would have to be provided for you, or you would have to be given everything else to solve for the KF value, okay? And then this last cursive EM is molality of the actual solution. So remember, that was just a concentration unit. So we've got concentration of a solution is the little squiggly m, KF is the constant, and then you can measure exactly how much the temperature freezing point was lowered by the presence of the solute, okay? So all of that can be calculated, all right? Let's talk about boiling point elevation, and then I'll give you two examples so you can see side by side, freezing point depression and boiling point elevation, okay? So boiling point, remember, got higher in the presence of a solute, and see here's the constant KB for water, okay? And it's the same units as the KF, but we're just putting B in there. Here's the formula given from your book. Delta T boiling, similar to the formula from the previous slide. This is the KB in parentheses first, and this is the molality, moles per kilogram, on the right parenthesis. Okay, so it's the same regardless of solute. As long as our solvent in this case is water, this would be the formula at the bottom. All right, so this is the increase. Okay, I want to make a note of this graph here. Now that you've kind of seen the pattern, remember, vapor pressure was lowered, freezing point was lowered, boiling point is raised. This graph has temperature on the x-axis and vapor pressure, specifically in millimeters of mercury, on the y-axis. And you can see this is pure water, the red line, and this is with solute sodium chloride. And you can see the increase or the difference in the two lines. Okay, so that is a way that you could kind of graph. We've went over strong electrolyte versus weak electrolyte. Strong electrolytes would have a bigger effect on whatever colligative property you're talking about than weak electrolytes. Weak electrolytes would look more similar to pure solvent alone. Okay, so let's compare freezing and boiling changes side by side. Let's just pretend I've got a solution where the molality is 3.60 mole per kilogram. Okay, it's a sucrose, so it's a sugar solution, but we're still mixing it in water. So I've got the Kf value I already gave you and the Kb value I already gave you. Okay, the normal values that I already showed you in the previous slides. Okay, so I'm going to show you the math of freezing point versus boiling point. So freezing point depression is what it's called, lowering the freezing point and raising the boiling point. Okay, so this sucrose will do the same thing, lower freezing point and raise the boiling point. Okay, so there's your formula, and I'll go ahead and animate in. Okay, so there's the molality times the constant, and that gives me delta T of 6.70 degrees. So from here, what you actually need to learn is not that, oh, okay, so now this solution freezes at 6.7 degrees. You need to go back to the freezing point of the plain solvent, which hopefully you know the freezing point of water in Celsius is 0. So if you actually look, the new freezing point is 0, the solvent alone, minus whatever we just calculated. Okay, so the new freezing point is negative 6.7 degrees Celsius. Okay, and then look at the boiling point. So if we calculate boiling point, remember this is the constant that's given, this is the molality. Okay, so you can cancel out your molalities and end up with degrees Celsius as your final unit. Whoops, excuse me. So the boiling point of water is 100 degrees Celsius. Add that same degrees Celsius value, and you end up with basically 102 degrees Celsius is the boiling point elevation. Okay, so we're going to look at osmotic pressure in a little bit, but I want to define osmosis first, which you should have learned. This is a new section. You should have learned osmosis in maybe a high school biology class or something, but let's just review it because it's focusing in on water. Okay, and then medically, we're going to go over what's kind of happening in dialysis and sort of throw in a new vocabulary word there. Okay, so osmosis, you're basically just looking at the movement of solvent, and in our world, we really are focusing in on water as that solvent, okay, across a semi-permeable membrane. Okay, so that's really, really important. Okay, so if you look, all these molecules here are just plain water molecules, all of the red with the two white spheres, and then this disc down here is the semi-permeable membrane, and then we have sort of pale blue spheres, and that is they call it here solvent particle, but you're thinking the same concept as solute. Okay, so basically water is going to move across the semi-permeable membrane, and that is osmosis, just the movement of, in our case, water is what we focus on. It's the movement of any solvent across a semi-permeable membrane. But the water is going to move so that the water is even on both sides. Since there is something else present in this image on the left side of the left image, there's something present in this side, the water's going to shift to the left, okay? And if you see, that is why the image on the right is showing after a certain amount of time. You see, initially, after a certain amount of time, the level of water is going to rise. So I know it's a little difficult to think of water as a concentration because we're always looking at concentration of something in water. But the water itself is saying there's not a balance of water on the right and the left because this water is crowded by whatever these blue spheres are. So the water will leave from the right and go to the left, resulting in the image we see on the bottom right of the slide, okay? And there's going to be a pressure here. That will be our osmotic pressure, okay? That will be the osmotic pressure, but we'll define that on the next slide and the following slide, okay? But I wanted you to know, make sure you're clear on what osmosis is, okay? This is the image from your book. So if that previous image didn't make sense, we've got a concentrated solution that's sort of green in color in the center here. And then the bottom, this very bottom, it's kind of an orange disc looking thing, or red disc, is semi-permeable membrane. So they're trying to zoom in on that in this circle at the bottom of the slide. So outside the blue, that's our pure, like H2O, pure solvent. You see that's labeled pure solvent, okay? So you should be thinking automatically, oh wait, which way is the water going to go? Is it going to go inside where there's a more concentrated, the green stuff, or is the water going to leave and move out? That's what you need to know. You need to be saying, okay, more concentrated solution inside, then the water will go inside because there's less water present inside. So over time, the water will enter in, and that's why you see sort of a more pale green. And do you see how this tube at the top is filled way, way high? That distance here is the osmotic pressure, okay? So they're trying to show the water flying in these green spheres, or the concentrated solution inside the container, very inside, okay? But whatever this value is here, that'll be the osmotic pressure, okay, which we can measure, all right? So just to recap, it's the amount of external pressure applied to a solution to prevent the movement of solvent across a membrane. So it's basically water's going to move until the water is happy. What does that actually mean? In short, this sub-bullet here, pressure required to stop osmotic flow, okay? So that is osmotic pressure. Once there's enough water on both sides of the semi-permeable membrane, there will be a pressure value, but osmosis will stop, okay? This symbol here is supposed to be the pi symbol, which I would write like that if I could find a way to write it in typing form, okay? So your book gives you the formula. Osmotic pressure is, the symbol is the pi symbol, okay? Osmotic pressure is equal to moles divided by volume times R, that we've already seen, the ideal gas constant, times T temperature, okay? So all of those are listed down here, but if your N over V, if you remember moles over volume, if volume is given in liters, which it needs to be because of the R, you could reduce that down to pi equals molarity times R times T, okay? So this lower formula here that I put the star next to is a simplified version. It's not provided in your textbook. This upper formula is the one that's provided in your textbook, okay? So you should be able to use this formula to solve for, as long as you're given all of the variables but one, you can solve for the other variable, okay? So that's the example that we're going to go to, but just so you know, we're gonna use this upper formula, the one from your book. We're gonna start by solving for moles. So you're gonna be given everything except the moles, and you need to solve for moles. And we're gonna read the problem, and it'll help you understand where we're going from there, because there's one more thing to know for the problem. Okay. So here's the example. So the osmotic pressure of a solution containing blah 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 blah. Hang on one second. So you've got the milligrams and the grams, and it's per 0.01 liters. The osmotic pressure was, and then there's the actual value. So pi is 0.0032 atmospheres. Okay, so that's your given. So start by writing your given so you're clear on that. And then we don't have the need for the mass yet, but we're going to get to it. You have temperature is 298 Kelvin. This was our formula that was reduced down, but you could do moles over volume. You have the volume, and you could solve for moles, okay? You have to, in order to solve for moles, this is a multi-step problem, you're going to have to get molarity and then use the volume. Use molarity as a conversion factor, okay? So you're thinking, all right, I've got these, get molarity, and from there, go to moles. I don't have an animation to show to moles. The question in the problem is actually, what is the molar mass of the solute of this unknown protein? And you're given a mass. So once you have moles, you can just divide grams over moles, and that would be the molar mass of the substance. So this is using a lot of knowledge from previous chapters and from the molarity earlier in this chapter. Okay, so first thing, I just rearranged this with the appropriate variables and plugged in all of the numbers. So there's the osmotic pressure, R is down here, 298 Kelvin is the temperature. That gives me my molarity. Remember, that is moles over liters. That big M means moles over liters. You need to know that for molarity. You just take that and multiply it by a liter value. Your liters will cancel, leaving you with moles. Okay, so I'm going to move that so that you can see. The reason that big M confuses students is you forget that it means moles over liters, so don't forget that. So now we have the moles of this protein just from the osmotic pressure given in the problem, okay? And the molar mass is simply the gram value given up top, so that gram value is right there. There's the moles we just solved, and that gives you the molar mass, okay? So it's a large molar mass, but that would make sense if I was dealing with a protein, 4.45 times 10 to the third grams per mole. That should make sense, okay? So I've redefined osmotic pressure here. I want to go over something about blood types, but you should actually know this probably from a biology class, okay? So this is the same pressure that I've already been defining and we just calculated with. Think about this in terms of red blood cells, okay? Because that's where you would actually apply it to medicine. Red blood cells have their cell membrane that is a semi-permeable membrane, okay? They need to maintain a certain balance of water inside and outside the cell and a certain pressure so that your cells don't burst or shrivel up into raisins, okay? We don't want that. So you need to know about the types of solutions that your red blood cell could find itself in and what's going to happen, okay, to that red blood cell. Is it going to swell up, or is it going to shrivel like a raisin, or is it going to do nothing? Okay, so you definitely need to know the three types of solutions, and these are listed here: isotonic, hypotonic, and hypertonic. Isotonic means that all of the solute that's in a red blood cell is equivalent to the solution outside. So you think of it as, I've got a beaker and I have a solution here, and then I put my, I don't know if I can draw a red blood cell very well, red blood cell in the solution. And what you want to know is what is going to happen to that red blood cell. Water is entering in and leaving the cell constantly, maintaining normal osmotic pressure. Well, in an isotonic solution, there is some solute out here, but it's equal to the amount of solute inside the red blood cell. So overall, the red blood cells look normal, and that's this image at the very bottom of the slide from your book. Okay, I'm going to skip hypotonic for a second and go to hypertonic because sometimes it's easier. So if you've all known a hyper person, that's like someone who's really high energy, hyper person, so high, think high solute. So what is something that's high solute? You want to think of high solute, so like syrup is really high sugar, high solute. So you're thinking we have a ton, so here's my red blood cell again. We have a ton more solute. So outside and the cell versus inside the cell, which means the water is leaving the cell. That's what it says in the bull here. Water goes out of the cells, okay? So if you put a red blood cell in a hypertonic solution, this is what they're going to look like. They're going to shrivel into raisins. The cells will shrink because water leaves. That's what happens when you go, if anybody's ever gone swimming in the ocean, your fingertips get all shrivelly because you're in high salt water, okay? If you can't remember crenation, that's another word for what's happening in the cells. Think like crumple, C, crenation, C, okay? They're crumpling up into raisins. Hypotonic is the opposite of hypertonic. It's a lower solute. So same concept. You need to think like you're in the beaker. If there is less solute outside, then water is going to move into the cell, and ultimately the cell is going to get, it's a little hard to tell in these images down here in B, but the cell is going to fill up so much that it's eventually going to burst, okay? And that is called hemolysis. So you may have heard the term lysis, but that's like bursting open. So you can actually kind of draw the red blood cell, and then it's like all broken out, okay? Bursting open. Okay, so you definitely need to know those three, and you need to understand what happens, who's got higher solute, who's got lower solute, that kind of thing, what happens to the red blood cell. Just one quick comment on dialysis, because your book mentions it at the end, but it's kind of like osmosis, but the word you would use is hemodialysis for patients. So people that need to undergo dialysis have non-functional kidneys. Your kidneys filter your blood. So looking at this sort of blue image on the right half of the image, what's going to happen is we have a semi-permeable membrane and then a solution that's going to enter in to this chamber, this blue chamber, okay? The blood, which is this sort of red serpentine shape, is going to go through that blue chamber, and all of the toxins that are in the blood that the kidneys failed to filter out are leaving. That's dialysis solution out, okay? So all the toxins are leaving, okay? But the person's blood is traveling this way, pumping through the semipermeable membrane, and then it's sent back in on the bottom here, okay? So that's just the way, just so you have the concept to know how dialysis works. They're filtering out using a semipermeable membrane, and then they're giving the cleaned out blood back to the patient so the patient doesn't run out of blood, okay? This is a summary image of Chapter 9, which was in the important Chapter 9 figures that goes through the colligative properties, concentration, in the very beginning, information, stuff that we've already seen, just so you have an idea all on the concept of Chapter 9, okay? So thank you for listening.